All right, let's continue our conversation about chemical composition. I want to introduce this concept of a basis of calculation, and we're going to talk about this more in class because this tends to be a very confusing concept. But basically, sometimes we want to know the mole fraction from the mass fraction. And so what we do is we assume what's called a basis of calculation. It's basically an amount that we're assuming is in the system so that we have the ability to relate mole fraction to mass fraction. And basically, to convert between the two, that basis of calculation needs to be something that makes sense. So many times what we do is we assume a mass of a mixture, so a 100 kilograms or 100 pounds mass. And then what we do is we use the mass fraction to calculate the mass based on the basis of solution. So let's say that the mass fraction was 0.2. Well, if we assume that there's 100 kilograms of the solution or the mixture, that means we have 20 grams of that thing because we have 20%. So 100 is a nice easy number that's easy to use. And basically what we can do is then we can say, okay, we have 20 kilograms, we can convert that to moles. And then if we then have moles, if we know the total number of moles, we can convert. So this is best illustrated by doing an example. So we're going to do example 3.2 if you're following, or sorry, excuse me, 3.3. So if you're following along in the textbook, it's 3.3-3 in your book. And basically we have a mixture of gases with the composition by mass. So we have oxygen, carbon monoxide, carbon dioxide, and nitrogen gas. And we have a percent of each of those. And we want to know what is the molar composition. So the first thing that we want to do in this type of a problem is we want to assume a basis of composition or a basis of calculation of 100 grams of the mixture. What this does is this allows us to say, well, each of those percents is now very easy to translate into a number of grams. So one of the things that's going to be really, really critical going forward is that we can convert from mass to moles, but we cannot convert from mass fraction directly to mole fraction. And that is very, very critical. So one way that when we do these calculations, if we're going from mass to moles, we have to think about, or excuse me, if we're going from mass fraction to mole fraction, we have to go to mass first, convert mass to moles using the molecular weight. And so there's a really nice way to set this up in what we call a tabular format or just a table format. So I'm going to step you through this step by step. So let me grab my laser pointer so we can chat. So here's the different components in the system, right? Here's all these different gases. And if we have a mass fraction of each of these, the mass fraction should total up to 1, right? We can't have more than 1 or less than 1. It's a fraction of the total. So if we're assuming that there's 100 grams of the mixture, let's take oxygen, for example. Oxygen has a mass fraction of 0.16. Well, we know that that is the fraction, right? And the fraction is the component over the total. So if we know the total is 100 grams, then we know that we have to have 16 grams of oxygen. Same thing goes for carbon monoxide right here. If we have 0.04%, right, and there's 100 grams total, well, that means that 4 grams of that total sample are carbon monoxide. And we can do this for the next two gases, and when we add them all up, we should get 100. Now what this has done is this has translated mass fraction to mass. And once we have mass, we can go to moles because we know molecular weight. So what we can do is we can go over to the periodic table and we can find the molecular weight of each of these compounds. If we have the mass and we have the molecular weight, if we divide the mass by the molecular weight, we can get the number of moles. That's great, right? So we can find out that for oxygen, for example, we have 0.3 moles. Now, in order to get a mole fraction, it's the same idea. A mole fraction is defined as the number of moles divided by the number of moles total. So what that means is that the first step in this fourth column here is that we have to add up all these moles so that we can get a total. So here's that total number down here. Now, if, for example, we want to find the mole fraction of oxygen, we would take the mole fraction itself, the number of moles of oxygen itself, divided by the total. And that's going to give us this number right here. And that's the mole fraction. So what this table is doing is it's going from mass fraction, which is X, to mass, which is M. We use molecular weight to go to number of moles, which is N, and then from N we go to Y, mole fraction. Now that can be very, very confusing. So take a pause and write in all those extra little words, right? Where are we're going? We can't go from X straight to Y. We have to go from X to M and from M to N before we can go to Y. And that's really, really critical because we're going to use those different variables throughout the semester. So take a pause if you need to make sure that that's really clear. And then the last thing here, right, is this is just kind of writing that out for you in a slightly different way, right? The mass of a species is the product of the mass fraction of that species and the total mass, right? So that's how we found mass. And then the number of moles is related to the molecular weight. And then the mole fraction is the number of moles of that species divided by the total number of moles. So take a pause and make sure that this concept is really clear. We're going to use this over and over again during the semester. Next thing that I want to make sure that we just hit very, very briefly is concentration. So you're going to see mass flow and molar flow and things like that, but as you get into upper level courses, you're going to see concentration. So there's a relationship between the two, and let's just talk about some concepts really quick to make sure that they're fresh in our mind from chemistry. So first is mass concentration, right? So this is the mass of the component divided by the volume of the mixture. And that's going to have units of something like gram per centimeter cubed. It could be kilogram per meter cubed, right? But it's an amount divided by a volume. We can then have molar concentration, which is the number of moles of component per volume of mixture, and that's something like kilomoles per meter cubed. We can also have molarity, and that is the molar concentration of a solute divided by specifically 1 liter of solution, and that's in terms of moles per liter or molar. So hopefully all of these concepts you've seen before in chemistry, but good to review here to remind us. The concentration of a substance in a mixture is useful for us because we can use it to relate mass flow to the total volumetric flow. Because if you look at the units of mass flow, that's kilograms per second. Volumetric flow is something like meters cubed per second. Well, the mass concentration itself is kilograms per meter cubed. So by unit analysis, we can actually use the concentration sometimes in very specific situations to convert between the two. So as an example, if we have 0.02 molar solution of NaOH and 5 liters of solution, we want to know what the molar flow rate if the stream is if it's flowing at 2 liters per minute. So if we have 5 liters of solution, 5 liters times 0.02 moles per liter is going to tell us that there's 0.1 moles in that particular system. If the stream is flowing at 2 liters per minute, and we have 0.02 moles of NaOH per liter, then we have 0.04 moles per liter flowing in the solution. So it's just a little quick, simple conversion. Last thing to talk about today is to just look at some other terminology that's important for environmental engineers. We briefly talked about a part per million in class when we did some in-class problems, and a part per million is defined specifically as the mole fraction times 10 to the 6th, and we can also have parts per billion, which is going to be the mole fraction times 10 to the 9th, so billions and millions. So we're going to see these terms throughout the semester. Remember that 1 ppm is equal to 1 milligram per liter, which means, 1 microgram per liter, which means that 1 part per billion is equal to 1 nanogram per liter. So that's something to be aware of. So let's take a quick little test your understanding. Let's say that we have a blood sample reported to contain 68 ppm of creatine on a mass basis, and we want to know what's the mass fraction in the blood. Well, we know that your parts per million is defined as your mass fraction times 10 to the 6th. So what we can do is rearrange and find that we're going to have 68 times 10 to the negative 6th kilograms of creatine per kilogram of blood. And remember, that's a mass fraction because it's kilograms of something per kilogram total. Then we can ask ourselves, well, how many milligrams of creatine are created in 1 kilogram of blood, contained in 1 kilogram of blood? Well, if we know blood's density is 1,060 kilogram per meter cubed, we can take that mass fraction, we can multiply it by the density, and we can do some conversions to find that there is 0.0721 grams of creatine per liter of blood. So we're not going to focus too much on concentration within the next couple lectures, but it is going to come up as we start to get into more elaborate mass and molar flow problems. So just keep these handy when we start to get to those specific parts of the lectures.